Hello everybody, this lesson is going to be about learning how the periodic table is set up. I know we've been using the periodic table a lot so far this year, but we're going to start learning a little bit more about its structure and some of the patterns that we can find on the periodic table. So first, I just want to talk a little bit about why it's called the periodic table. You don't have to write this part down. You should listen to it so you understand some of the things we'll talk about later. The word periodic means something is happening at predictable, regular intervals. And so the idea of something happening in a predictable fashion led them to come up with the periodic law. The periodic law helps us figure out how the physical and chemical properties of the elements are going to be based on the pattern of where they fall in the periodic table. There is a predictable and regular pattern to them. And what we were going to be learning is that it's based on their atomic number. And so once they realized that the elements were showing this predictable set of patterns, they were able to arrange them based on the atomic number to really highlight and make those patterns more easily accessible to us. We can look at where an element is and figure out what its properties are most likely going to be. Another thing that I want to go over real quick is just the term element. An element is a pure substance. It's kind of the smallest piece that we can get with things behaving in the way they should. If I take an atom and I break it into protons and electrons, it's not going to behave like the atom anymore. So when we're talking about an element, we're talking about one kind of atom. A compound, molecule, when we start putting multiple atoms together, is not something we're going to see on the periodic table. It's the periodic table of elements, so the singleton atoms by themselves. There's roughly 90 that occur naturally on Earth, and roughly 25 have been synthesized. I probably should update this. Nowadays, there's probably way more than 25 that have been man-made. So that might be something I should go back and do one of these days, is look up the most recent number and see, because it seems like every year they're finding more and more elements that they've made. We now have all the way up to 118 on our periodic table. One thing I think is neat to learn is that there's a lot of different periodic tables. A periodic table is just a way to organize your elements to show patterns that you're interested in. The thing that we look at and think as the periodic table is just the one that's the most commonly used. It's one that shows the most common patterns that most people would be interested in. But it's not the only one. Some of them look really crazy. You can see some examples here. Some of them look like circles, some of them look like towers, some of them, I don't even know what this would look like. Really strange shapes here. This one kind of reminds me almost of a fish or something. This one has kind of a neat shape, almost like a spiral and an oval. I like showing you these different examples because I think it's important to realize that the periodic table is a man-made invention. We just decided where we think things are useful to be put on our paper so that we can quickly find information. It's not a one correct layout. So depending on what you're doing, what type of research, maybe somebody likes to use a different type of periodic table. Let's talk about Dmitri Mendeleev. So he was the person who started to group the elements according to their atomic masses and the way they behaved, their properties. So he was the person who kind of gave it the best first attempt. He was almost right, but not quite right. So one of the things that's pretty impressive, though, is how close he came to getting it correct. So this is a picture of Mendeleev's published periodic table. It doesn't look like what we're used to. It doesn't have all the little boxes. It's not lined up the same way. But you can see that he was trying to group things, in columns and was trying to figure out how they would behave. One of the things you should notice is that there are some question marks on here. When he started laying out his patterns, he realized that there had to be missing elements if his patterns were to make sense. He knew that there were elements that maybe weren't discovered yet. And what he did is he literally published his paper with a placeholder for these elements. He put the question marks here, telling people that there should be elements here that we haven't discovered yet, that his patterns made so much sense that he could predict that they existed. And he got really close to accurate. So here's an example. In the orange over here was his prediction. He called it ecosilicon. He thought it would have a mass of 72, and it has an average mass of 72.6. That's pretty close for a guess. He thought the density would be 5.5, and it was 5.47. Bonding power is how many things it likes to bond to. It likes to make 4 bonds, and it does in real life. He thought it would be a dark gray. Turns out it's a little bit lighter of a gray, more like a grayish white. And we call it germanium now. But considering the fact that in 1871 he was just guessing what this element would be like, that's pretty good guess. Henry Moseley came along a little bit later and realized that Mendeleev was so close to correct, but instead of organizing it by the mass, it really should have been by atomic numbers. And so that was the big deal of what Moseley did, was he changed the periodic table to go by atomic numbers. And there were just a few elements here and there that got switched. And once they got switched, the patterns worked much better. So he determined that, okay, this atomic number, the number of protons, is how we should set up the periodic table. And it's still not perfect. There are still places where our patterns don't work. If you remember when we learned electron configuration, right, we had some places where things got really weird really fast, but it's pretty good. It's good enough that we use it in chemistry every single day. So there are different ways to kind of divide the periodic table based on the properties. And one of the biggest ways is by what we call the classes of elements. So one of the little glue-ins that you have for your notes is a little teeny tiny periodic table, and you can color code this. Most of this periodic table, you see this light blue color, are metals. The red ones are nonmetals, and the ones along this zigzag in green are called metalloids. Sometimes you may hear them called semi-metals. Once in a while, you may see people call polonium a semi-metal. Down here towards the bottom, it gets a little bit debatable. I would never ask you about polonium. It's just a little bit too hard of a question because it would depend on which properties you were looking at. The rest of them that you see, totally fine to call metalloids or semi-metals. One thing to notice over here, hydrogen, even though it's in this first column, is not a metal. Okay, so that's something you need to be careful of. Another thing you can see on this periodic table is that, do you see how mercury down here, number 80, and bromine, number 35, are in blue font? That's because they're liquids at room temperature. If it's a black font, it means they're solid at room temperature. Blue font means that they're liquid at room temperature. And the ones in white are gases at room temperature. So later on in the year, we'll learn a little bit more about that. Here are some properties of metals. We have chemical properties and we have physical properties. So let's do the chemical properties first, and then we'll come back and we'll do the physical properties. So metals don't have very many valence electrons. Remember, those are the ones in the most outer shell of the atom, the highest energy level. Because they don't have very many electrons in that outside shell, they lose them very easily, and they like to make positive charge ions, which we call cations. We learned about that when we were learning how to count our protons and our neutrons. Physical properties, they're ductile and malleable. Ductile means you can pull it into like a wire. Malleable means you can bend it and shape it. They're actually different properties, even though they seem pretty similar. When we say they conduct, we mean that they conduct electricity and heat. That's why you don't want to touch the handle of a pan on the stove, because it can conduct the heat. They're shiny. Sometimes they may not look shiny because they may react with oxygen that's in the air to make a coating on it that's dull. We call that an oxide. Usually the most famous oxide that you're used to seeing around would be rust. Iron oxides turn that brownish red color. If it's a copper oxide, it kind of turns a greenish color. But if you were to sand that off or cut it apart, you would see that it is shiny inside. And almost all of them are solid at room temp. If you remember from the previous slide, there was one metal that's not a solid, and it's mercury. All right, let's look at some of these Bohr diagrams for a minute. We don't use Bohr diagrams for very many things, but it works pretty well for what we're talking about here. It's simple enough that we can use Bohr diagrams. So if you look, this is beryllium, and beryllium only has 2 electrons in its outer shell. Sodium over here only has 1 electron. So it's pretty easy for it to get rid of those. And then it would drop down to this next level, which would be nice and full. That's why sodium likes to make a +1 charge. It would be more stable. Let's look at nonmetals. Same thing, chemical properties, physical properties. So nonmetals have almost full or totally full valence shells. They prefer to gain electrons, which gives them that negative charge, which we learned we call an anion. Nonmetals are not ductile. They're not malleable. They don't conduct electricity or heat very well. Usually they're solids. Sometimes they're gases. Let's look at these Bohr diagrams. We have oxygen, fluorine, and helium. So you can see down here for fluorine, we have 7. 8 would be full, right? If it had 8 electrons, it would look like a noble gas. So the fact that it only has 7 means it's very close to having a full shell, so it's more likely to make an anion by gaining an electron to fill this missing spot here. Oxygen has 6. So it would like to gain 2 electrons. It's almost full. Helium always throws people off because they say, oh no, it only has 2 electrons. That's not very full. But you got to remember that the first energy level, that 1s orbital, can only hold 2 electrons. So 2 is full for helium because that first energy level is just so tiny. Metalloids or semimetals are the ones that are just kind of in between. They have kind of a half-full shell. They can make anions or cations depending on what's going on. Some of their properties are like metals, some of their properties are like nonmetals. I would never expect you to know which is which. Okay, I would never ask you, which properties of silicon are metallic and which properties of boron are non-metallic. I wouldn't do that. It maybe would be something you could look up. I might ask you to research it or something, but I wouldn't ask you to know specifics about elements, just the general characteristics of the classes. Whoops, that direction. There we go. All right, so you can see boron has 3, which for it being such a small atom is kind of half full. It could go to 8, but it really doesn't want to. It's pretty small. And you can see here, silicon has 4, which is right in the middle. It's in that carbon column, which likes to make plus or minus 4. The next important thing about the periodic table is knowing how to count what we call the periods, or the rows. They go horizontal. The way I always remember that is you put a period at the end of the sentence, and our sentences go left to right. So that would be period 1, 2, 3, 4, 5, 6, remember the F block is inside there, and 7, remember F block is in there. So we only have 7 periods because we have 7 energy levels. When we're doing our electron configurations and we have to worry about going from 4s to 3d and back to 4p, right, that gets a little bit tricky. But if I ask you what period something is in, it's very straightforward. It's literally which row number. There's no funky numbering here. It's just literally top to bottom, 1 to 7. So we have 7 periods on the periodic table. Some of the properties of the periods, we have 7 of them. As you go left to right, their atomic numbers increase, and almost always their mass increases. Not perfectly, remember that's what Moseley figured out, but almost always. The other thing that's interesting about the periods is that all elements in the same period have the same number of energy levels. If it's in period 1, it only has 1 energy level. If it's in period 2, it has 2 energy levels. If it's in period 3, it has 3, and so on. Remember, energy levels and orbitals are not the same thing. Energy levels is the bigger, broader category. So you can figure out which period something is in if you can tell how many energy levels it has. That's one of the things that's nice about those simple Bohr diagrams. So we can look at these and figure out that this one must be in period 2 because there are 2 energy levels. Same with this, 2 energy levels. Must be period 2. Down here we can see that there's 1, 2, 3. This one has 1, 2, 3. So these must be in energy level 3, period 3. They match. Groups or families go up and down. The reason they used to call them families is because people in a family tend to maybe look a little bit alike. They have some characteristics or maybe some behaviors that are the same, but they're not identical, right? You may look a little bit like your brother or sister, but you're not identical. I suppose if you're an identical twin, that's not true, but you know what I'm saying, right? So the idea here is that all these elements in this group will have similar characteristics. They will have similar behaviors, but not identical. That's why they called them a family. That's a little bit old-fashioned of a name. We usually call them groups. So going all the way across, one of the things that's weird is that we really don't count the F block this time. We just ignore it. So we say there's 18 groups. Why we count it for the periods and why we don't for the columns, I mean, I don't know. It's one of those weird things that's just stuck around over the years. So we would say that there are 18 groups. The atomic number and the masses increase as you go from the top down, which makes sense, right? You're getting way more protons, way more neutrons, way more energy levels, way more orbitals. Everything in the same group has the same number of valence electrons. When we were color coding and labeling our periodic table, when we were learning our configurations, we learned that everything in column 1 likes to make it +1 because it has 1 valence electron to give away. Column 2 has 2 valence electrons. Column 3 has 3 valence electrons. The D and the F block don't follow those rules. The reason the things in the same group or the same family behave the same way is because they have the same number of valence electrons. If you think about it, when two atoms bump into each other, all they can really see and interact with are the valence electrons because they're the ones on the outside. And so if the electrons on the outside of the atom are the ones involved in bonding, then that's what's going to give it its behavior and its properties. The joke is that atoms are shallow, they only care about what's on the outside. It's because those valence electrons are so important. When we start learning to draw molecules and learning to draw single bonds and double bonds and triple bonds, we will only be drawing the valence electrons. They're the only ones we're going to care about. So it becomes fairly important. So you can see here's hydrogen. It has 1 valence electron. Here's lithium. It has 1 valence. Here's sodium. It has 1 valence electron. So everything in this column, everything in this group, everything in this family, all has the same number of valence electrons. Because they have 1 valence electron, I know they're in group 1A. Remember we have that weird A and B numbering system? We go off of the 1A, 2A, 3A, all the way to 8A, because those are the ones that follow the patterns better. We don't care about that D block. We don't care about the F block. You can identify elements based on being told their group or their period. So for example, if I say group 14, period 2, you know it's this column right here, and you know it's period 2, so it must be carbon. It's kind of like that battleship game, right? Where you have to use the coordinates to locate something, right? It's what we're doing here. It does get a little bit tricky because sometimes we may use the A and B notation, and sometimes we may just go 1 to 18. But, if I told you group 3, period 2, this wouldn't make sense, would it? There's no element here. I must have meant group 3A. Okay, so it'll usually be pretty obvious if they're talking about the A and B notation or the 1 to 18 notation. All right, let's try another one. Group 2, period 5. Strontium. Group 2, period 5. All right, you try this last one on your own, okay? Period 6, group 17. Sometimes we mix up the order. We don't always say the group first. Period 6, group 17. There we go. Astatine. Okay, sometimes people will say, is it astatine or astatine? I was always taught astatine because if you think about it, it's fluorine, chlorine, bromine, iodine, astatine. Okay. All right, so just to recap real quick, we should have learned that there are 3 classes of elements: metals, nonmetals, metalloids. We should have learned the properties of each one. We should have learned that there's groups and periods, that the periodic table is organized nowadays by the atomic number, the number of protons, and that Mendeleev was almost right when he arranged it by mass. We can use the periods and the groups to learn information about the atoms, like how many valence electrons they have, or what charges they like to make, or how many energy levels they might have. So we can learn a lot based on their position in the periodic table. All right, everybody, that's it for this part. There will be more things we'll learn about the structure of the periodic table, but that covers some of the intro things about how we locate atoms, and we'll use that information later on in the chapter. All right, bye everybody. Hope that was helpful.